Okay, perfect. So I'm going to present you CREME, which uh, from what Dennis showed just earlier, appears to be popular, and that raises the bar quite a bit. So I'll show you some first results that we have. I mean, truly first results. And I will also show you at the end the engagement that we need and with the start of meetings that we are about to have. So this has been delayed for different reasons, and but it's starting now. So I'll show you a few slides from last year because they are really important just to be on the same page. First of all, terminology. There are people discussing about different periods of Earth, and they use different words. And we ended up in this table here that when we say modern, we mean something like either pre-industrial or present, but something fairly close to our lifetimes. And then present day literally means now or about now. And then pre-industrial is established that it always means 1850. So what we're going to be doing in CREME is to simulate the pre-industrial Earth with an asterisk, and by using different planetary models that are not designed to simulate pre-industrial. But you know what? That's the only time that we actually have some data to compare against. And to be honest, it is present day that we have even more data, but we would not expect that models for other planets are already incorporating things like humans or plants or something like that. I'll get to that in more detail later. But the important thing is that we say if you want to benchmark your model against something that looks like a measurement, you should be doing pre-industrial Earth and really nothing else. Because the further away you go from pre-industrial Earth, the data becomes more scarce and the error bars becomes like humongous if you even have data. Other terms are paleo, which are mostly for the more recent Earth's history, so the oxygenated past of Earth, really. And that would be like up to a few 100 million years ago, till pre-industrial. Early Earth is something about the distant anoxic past of Earth. So Archean is the most common thing that you see, that you mean when you say early. It can be the boring billion, can be the Hadean, but it's something like in the billions of years ago. And the sun is quite dimmer. I mean, obviously, the further back you go, the more dimmer it gets. So for paleo simulations, we do simulate a dimmer sun, but it's not that much dimmer than when we're thinking about early Earth. And then we have the compromise, which is touching a lot on what essentially Linda said. If we want pre-industrial Earth and simulate that, what we need is really population of 1850, crops, land cover, vegetation, everything related with that. And we do understand that this is not necessarily the goal of many, many models out there for exoplanets. And for that, we decided that we will take a step back and say, okay, let's say pre-industrial with no life, and then do our best to simulate that. And I'll go into more details on that, and I will even show you some results about that. And then in terms of model configuration, we have two different words that we will be using a lot. One is that if you are prescribing something, so let's say you have the sea surface temperatures and you say, I have no model that simulates the ocean. So here is data for what the sea surface temperature is. And we know that up to a good extent about the pre-industrial Earth. And the other word is dynamic or prognostic, and which essentially says that the model is calculating the variables that are of interest. Can be really anything. I mean, the model calculates things like, global temperature, whether it is 3D or 1D or just a column or an energy model, balance model, the global mean, doesn't matter. But if something is calculated by the model and is affecting the following time steps, then that's a prognostic or dynamic variable. So I kind of said why to compromise, but we have this planet and it is really, really complex. And there are some issues like topography. If you have a three-dimensional planet that has certain topography that is complex, then if you are going into simpler models, or even if you are going into simulating exoplanets, we have really no idea about topography there. So either because you cannot simulate it, or because you don't know whether what you are simulating makes any sense for any other planet, then topography is something that is going to be a challenge. Another thing is the oceans. For the most part, when we're trying to simulate an exoplanet, we don't even know whether there is an ocean or not. So models are using some simple parameterizations for that, and I will touch on that a bit later. But it's one of the complex things that dramatically affects the output that we'll be getting, but we don't know much about it. And then the most complex thing of all is life. And that was an easy decision. If you want to be inclusive and you want CREME to actually have a lot of models rather than like three, then you should really kill all life. And we have ways to go from, I said that we'll have measurements from pre-industrial, or we know it to a good extent how pre-industrial looked like, but that is in the presence of life. But we can use complex models to infer what that planet would look like without life, and I will get back to that. So in terms of capabilities, if you want to be really as close to perfect as possible, you would need to simulate the ocean dynamics dynamically. So simulate the sea surface temperatures from the climate system input. You would be using certainly the bathymetry of Earth, because we're talking about the pre-industrial Earth simulation. And you would be also calculating the sea ice. In terms of land, you would be using the topography, vegetation, and land ice of Earth. And ideally, other than topography, which doesn't change really, you would like to have those dynamic, but very few models are having dynamic vegetation, truly dynamic vegetation, and even less models have dynamic land ice. So it's okay if you prescribe those. In terms of the atmosphere, we go for 1850 conditions, and I'll go into more detail in a minute. And then ideally, you would have people, and then the star will be the sun, obviously, and the orbital parameters will be those of Earth. So that would be the perfect model to simulate pre-industrial. On the other end of the spectrum, we have the insufficient models. Frequently, it has been used, too frequently, to be honest, that if there is an ocean, there is a zero heat transport across the latitudes. And we know that this is probably not happening really. And so we cannot have a model that simulates that and compare it with the pre-industrial Earth, because it is far from reality, and it also has a tremendous effect on the planet's climate. Then for the same reason, if you say there is no sea ice because you cannot simulate it, then it's not a good idea. We cannot do that. Topography has to be that of Earth, with compromises depending on whether the model is 1D, 2D, 3D, but it has to resemble Earth somehow. And then the land ice should exist in some sense. I mean, you need to have a cryosphere. If you cannot have land ice and you have snow that accumulates, that works, okay, but you really have to have ice. The atmosphere really needs to be 1850, no question about that. And then you really had to simulate the orbital parameters of Earth and the star being the sun for the present day sun. So these are the things that you really cannot get away without. So the compromise is something in between. We have the dynamic ocean ideally, but you can prescribe it. If you have a model that has the Q-flux ocean, then you need to have the Earth's Q-flux values, not zero, and then that's okay still. Same thing for sea ice. It's okay if you have land ice being snow, as I said, and the compromise would be no people, no vegetation. And if you really want to participate in CREME, you need to at least get the entry ticket for the compromise. If you can go further into pre-industrial, that is even better. So that's the atmosphere. I have some numbers here. I'm not going to go through them. Um, the the assumptions are pretty simple, and I think that most models that have an atmosphere, they are able to simulate that. I am not certain about things like N2O, whether the models have them or not. I want to hope that this is not a roadblock for many models, but we will discover that as we go. And how do we do this? So everyone runs the compromise setup, and I really mean everyone. Even if you have more capabilities, we have to have a certain benchmark case. And then if you can do more, you do pre-industrial. But be careful, don't use any Earth-centric hacks, and every model has those. If they are participating in CNIP, take them away. If you cannot do pre-industrial, but you can do better than compromise, then by all means do that. And again, no Earth-centric hacks. And try to go as close to pre-industrial as possible, that based on how your model allows you. And then continue to do that. And then you can do stepwise backwards as well. So in terms of going stepwise backwards, between pre-industrial and compromise, you can have several configurations. So you can go from pre-industrial, and then let's say you remove vegetation, and then you remove land ice and you make it snow, and then you remove humans as well. I mean, the order can be whatever. And then you are approaching compromise. Or you can go in one step, or you can go in fewer steps for one model and more steps in the other model. It doesn't matter. The important thing is everybody does compromise, and then we have a range of models that are able to do either pre-industrial or the individual in-betweens. And then we have data points to compare against. And then the measurements are in pre-industrial. If we have a couple of models that can simulate really in fine detail, moving backwards in complexity up to compromise, then we can see, model dependent obviously, how you start deviating from the actual measurements, and then you would know what's your baseline that would make sense to compare against your compromise. So if you take, for example, land plants, and you see it like a drop in your model's temperature by a number of degrees, then you would expect, and if you see that in a couple of models, then you would know that the compromise needs to be a bit colder, and that's okay. So this is the game we have to play here, essentially to see how far off the measurements we can go based on what we expect from the complex models that became simpler to simulate the compromise setup. I just said that. And then we compare all models using compromise benchmark. So an example with Rocky 3D, which is what we try to do. So you can see here a simulation of the exact pre-industrial. The red line shows a long spin up. It has run for like 1,000 years, maybe even 2,000. I don't remember exactly. And then the green line is something like a continuation of that spin up. So you see the model, top left is the net planetary radiation, needs to be as close to zero as possible to be in radiative balance. It's very good. Surface air temperature, it's you can see it on the top right, and then ocean and lake ice coverage in the bottom left, and total cloud cover in the bottom right. Everything looks very nicely equilibrated. The thin line is the annual means, and the thick line that has less variability is the decadal means. And you see that the model is very nice and stable and simulates values that actually make sense. And then what you can do is that you can say, okay, this contains some Earth-centric hacks. Let's take them away. And this is what it happens. Again, we start from the tail end of the red line, and you see that the model changes. If you start from the bottom right, the cloud cover is increasing a little bit. I mean, we're talking about 1% here, right? It's nothing major. And then that leads to more reflective radiation going out to space, and that leads makes the net radiation of the planet become a little bit negative. Surface air temperature goes down by like a degree or less, even when it equilibrates, and that increases land and sea ice. Everything looks fine. And we're talking about exoplanets here, right? So a degree, give or take, or 1.5% for the total sea ice is within the noise, well within the noise. And then we say, okay, let's make it a step further. This is the Earth's vegetation cover, and it doesn't matter which one is which in those panels, but what you can see is different vegetation covers across the Earth. And you can see also the bottom right final two ones are two different types of bare soil. So you can see Sahara standing out, for example. And so we say, okay, this is what we are using. Let's simplify that. Don't eliminate it completely. Do it one step at a time. And then just say that across latitudes, which are essentially similar climate zones in general, let's say that across latitudes, we average out all the vegetation. And then you get something like that, which clearly doesn't look like Earth anymore, but it doesn't matter because it's a simplified version of what vegetation looks like. And then you say, okay, let's go see what that does. And that's the blue line here. And it doesn't differ that much from the yellow one, right? So clearly vegetation matters, and especially if you look locally or regionally. But if you keep the same plants in the same climate zones that they belong to, which are defined by the latitudes because the Earth is a fast rotator, then you can see that the results are not changing dramatically. So, okay, good step. So we know that we are not going too further away about assuming some simple vegetation. But so the next step for us would be to take away vegetation completely and see what happens then. I don't have results for that right now. So we are also looking at links with other MIPS, and the Philae is one of them. We know that the energy balance models don't have longitudes, so this is one of the reasons why we started thinking about this flat vegetation idea. The other idea would be that if you change the obliquity, for example, of the planet, then you are changing the climate zones, so you might need to adjust your vegetation because of that. Energy balance models also have difficulties in saying what topography is actually that of Earth. And by not having longitudes, if you have Africa and South America, they cannot tell whether there is an ocean in between. So you really generalize what the topography looks like, and that includes also the height of the mountains, which also play a major role in the climate system. Same thing about the ocean, and transport is parameterized in the absence of longitudes. Clouds are parameterized, and I am certain that some energy balance person can say many more, can add a lot of more bullets here. So we'll have to think how to link that. And going into pi, they only have altitude really, and that includes additional complexities like the solar zenith angle is a latitude of a proxy, is a proxy of the latitudes, but it can also be a proxy for day and night because they don't simulate really diurnal cycles. And but there are a lot of things here that we can discuss. And for both Philae models and pi models, the important thing is that they parameterize things like transport, for example. The more complex models, like the three-dimensional models, can provide information about what transport makes sense for a certain type of a planet. And not only for pre-industrial Earth, but for any planet that a complex and a simple model can simulate. So we might find some really important synergies here. And instead of saying that pi models need to approach the 3D models, maybe they can just get input from the 3D models. A lot of things to discuss here. So where we stand, scan this barcode and tell us when you're available. The meeting will be in mid-November. We have 2 weeks there, and we hope to find some really big participation. And then I guess that we will be getting those presentations shared, so you will have that barcode as well. The current status is that the paper is being drafted, though that's a straight lie. I have a paper that started drafting like a year ago and haven't touched it for quite a bit, but there is a document that has started existing. We have a final list, a list of participating models and modelers. We have a quite extensive list of those that we will be reaching out and make sure that they reply to this kickoff meeting and they participate. We have started discussing for the links with other MIPS. So Pi is Sunny Harman and Philae is Rory Barnes. We have a number of future directions. I'm not going to expand on that. I mean, this will be like we publish the protocol and then we can use the protocol for a lot of different things. And of course, run parallel simulations with other MIPS. I think that's it. Yes. Thanks. That's it. And I'll take any questions.
Thank you, Kostas. There are two questions in the chat. Otherwise, feel free to raise your hand and unmute yourself. Thomas, do you want to voice your question?
Yes. So, and it's just, I was wondering for the albedo, specifically something like the eye. So I know that different models don't have necessarily the spectral dependency for the albedo. So are you going to prescribe that a simple albedo for those cases, or?
I would prefer to not prescribe the albedo because different models will have different surface temperatures and the sea ice will not be the same for all of them, or the land ice or the snow. If there are many models that really cannot do that, then we might need to think a bit harder about it. But my first reaction would be that I would like the albedo to be prognostically calculated rather than prescribed, even if that means that it increases the range of results from the models. But if that excludes many models, then we might have to think about that again.
Okay. Yeah, you have the spreadsheet maybe, right? With different models and asking the modelers the question about the capabilities of their model. Can they do that or that?
Yeah, that we will be having a table that includes all the details about capabilities, absolutely. And that will essentially tell us how to decide on the compromise setup.
Okay, thank you. All right, so we have a question from Alejandro, sorry. Do you want to read it out loud, or otherwise I can do it?
I can go ahead and do it if you can hear me.
Sure. Yeah.
Hi, Kostas. Thanks for presenting this, and the work you guys have been doing has been really great, and I think this is awesome. I understand your plea to like remove the Earth-centric hacks. A lot of those are shortcuts that people take at times because their science allows it, but there are things in a lot of these models, as you know, particularly the three GCM models, where you're running up against the closure issue with any sort of fluid. You have to make a decision about how to close the equations because there aren't analytical solutions. And but there's also often not obvious physical arguments to choose where to close that, you know, a group of us would ever agree on. I'm just kind of curious at that point, how are you guys thinking about what guidance to give about how to report that, to keep track of those changes and decisions? In my question, I use an Mono-Obukov closure as an example, but I know there are others riddled throughout these models. Because at some point, I guess, you can remove as many hacks as you want, and someone else will still come along and say you still have a hack in there. So I guess, how are we going to capture that so that we can understand the comparisons and the differences that might lead to subtle changes in results?
Right. So that's a tough one. And I would make it even harder that by saying that there is a good chance that modelers might not even be aware of whether there is a hack someplace in the model. So that's a real thing. And I would say that we have to remove certain things that are really obvious. If you are simulating, for example, ocean currents, and you have a hack that says, here are where the tides are happening because we have the moon and the sun and whatever else that affects the tides in the ocean. And I would say remove that, because yes, you are trying to simulate present day Earth, pre-industrial, but but really you are trying to simulate something that is a generalized planet. So you should not be assuming the gravitational environment of the Earth by adding externally something like that. Another example would be in Rocky 3D, for example, that I know well, we have a correction on the vertical heating profile of CO2 because of, I have no idea why. So you really should not use that, because this is something that says that, yeah, this is Earth, and over Antarctica, this is happening, and you should correct that. You cannot have something like that, especially anything related with information that has a spatial dimension, which implies that you know that something happens in part of your planet, and you are correcting that to be more accurate. You should not have that. Closure is a very difficult one. So yeah, if you need to have some code that to maintain closure, I think that's important. You probably cannot take it away. But in general, I would say the generic answer to your question would be, I am a very big fan of a case-by-case studies. So I would like to hear every model which things it has that it considers hacks, big or small, and then we can see whether it makes sense to remove them or not. So in our case, for example, we have a gravity wave drag for the stratosphere that is tuned against some Earth values to get some proper wave propagation and who knows what else in the stratosphere. And we have a simple one that we know it performs kind of okay. So we say, okay, we'll use the simple one. And so other models might not even have a simple one. They might only have the one that is really based on Earth, and there is nothing else you can do about it. Then, well, you know what? Bad luck. If this is what they're using for other planets, I'm okay to accept that, as long as they really don't have something more generalized. It's really a balance. At the end of the day, we will have to be the ones that are implementing the simpler parameterizations. And if one doesn't have a simple parameterization, then that's okay. If that's what they are using for other planets, fine with me. So to elaborate even more, if you take the type parameterizations, for example, that models had, or the Proxima Centauri B and the planets, and if you can use that exact model version to simulate pre-industrial Earth or the compromise setup, then I would say that this is totally fine to keep that. And if you have used some Earth-centric hacks in Proxima Centauri B planets, then keep using them, sure.
Thank you, Kostas. Are there any questions or comments? Nothing in the chat. In that case, let's move on to the next talk, which will